All right, so the probability, we're looking at probability rules. Probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. All right. All right, so the law of large numbers. As the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So, in other words, the more times you run your experiment, the more accurate your outcomes, the probability of your outcomes will be. So, in other words, well, I'll give you an example in a few minutes, but they gave it to us in this order, so that's why I'm giving it to you. Law of large numbers, the more times you run your experiments, the closer you'll get to the actual probability of your outcomes. All right. All right, so an experiment is going to be any process with uncertain results that can be repeated. So an example of that is flipping a coin. Your sample space is the collection of all possible outcomes of an experiment. So an example of that with reference to flipping a coin is heads and tails. Also, your sample space is normally denoted by capital S. All right, an event is just any collection of outcomes from the sample space. So if I want to know what's the probability of landing tails, then that would be the event. And that's normally denoted by a capital letter. And you probably wouldn't use S because S will represent your sample space. All right. I'll just going to go here. Um, Before I go to computing probability, let me do two rules and then we'll get into computing. Sorry about that. Okay, two probability rules. One is that whenever you see P parentheses capital E, that just means the probability of event E. So if you had a capital A in the parentheses, probability of event A, and so on. But the probability of your event has to be in between 0 and 1 inclusive. It is possible for it to be 0, it's possible for it to be 1, but it cannot be larger than 1 or less than 0. Then when you add up all of the probabilities of each one of your individual outcomes, they are supposed to add up to 1. All right, so probability model is a list of numbers or list of probabilities that must satisfy the rules 1 and 2, the ones we just finished mentioning. So next example says verify that this is a probability model. So if I'm not mistaken, let me go back. Yep, this is referencing M&Ms and the probability of getting a brown, yellow, red, blue, orange, or green M&M in a bag. All right. So first we need to ask ourselves, does it fit rule 1? I won't say value, I'll say each probability. All right, so each probability is between 0 and 1. And then rule 2, when you add up your probabilities, does it add up to give you 1? So we got 13, 13, 16. So that's 40, 60. Yep. Hold on, I'm missing one number. 13, 14, 13, 24, 20, 16. Yep. All right, so they add up to give us 1. All right, so since the probabilities satisfy rules 1 and 2, it is a probability model. So remember rules 1 and 2. Rule 1 is that each probability is between 0 and 1. And then rule 2, do all of them add up to give you 1 individually? And that was the answer. The answer was yes for both of these. An event is impossible if the probability is 0. An event is a certainty if the probability is 1. The closer a probability is to 1, the more likely the event will occur. All right, so the closer a probability is to 1, the more likely the event will occur. The closer a probability is to 0, the less likely the event will occur. An unusual event is an event that has a low probability of occurring. And then we have our cutoff point. All right, so typically an event with a probability less than 0.05, or in other words, 5%, is considered unusual. Now, that's not set in stone, but that's what we normally use. So, but as far as the book is concerned, when we go further and we talk about being unusual versus usual versus unusual, that will be our cutoff point, and they're just talking about for your own testing. Um, that's not set in stone. All right. So now let's look at All right, so the empirical approach to calculating probabilities, you take the frequency of your event and place it over the number of trials of the experiment. So in this example, an insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim. Based on these results, what is the probability that a teenager will file a claim in a given year? So all you would do is take that 24, which is the number of people filing the claim, number of teenagers filing the claim. That's your event. Place it over the total number of teenagers that you have, which is 182. And that's going to be 0.132, probability of 0.132. And you may see in my math lab these type of options for an answer. So what this will state, or what we could use, say, all right, so my math lab may give you this type of statement as a possible answer. So for every 100 teenage drivers, we expect about 13 to have to file a claim. So what does that mean is that what they did was they took the 100 and multiplied it times the 13, the point 132, and that would be 13.2. So that's where they're getting that 13 from. So whatever this number is, if you take that and multiply it times the probability, that's the number that they're getting right there. So just in
Do
case they,
normal
hmm?
do normal rounding rules apply here?
My math lab is going to give you an option. If they go there, they're going to give you a statement. They're either going to want just the this as an answer, or if they give you a statement like like what's in the purple, you would just
Uh-huh.
take that 100, multiply it times the probability, and whatever number they give you that's close to it, that's what you're gonna go with.
Okay, all right.
You know what I mean? So it'll be in the statement. You know.
Got you.
Mhm.
All right. Thank you.
Yep. So in other words, let me go here too. Let's say if it said for every 100 teenage drivers, we expect about 20 to have to file a claim. We know that's wrong because there's no way to go from 13 to 20 in any type of rounding. So that's what I mean. They'll give you the numbers in there and you just pick the right number. All right. So let's look at so going back to this style, the empirical rule, all you do is put the frequency of your event over the number of trials. Classical approach, or the classical method. All right, so the classical method is you take the number of outcomes in event E and place it over the number of outcomes in your sample space. So if we go back to flipping our coin, and let's say we flip the coin and we want to land tails. So the first thing we do is examine how many outcomes are in our sample space. And we know that's heads and tails. So the number of outcomes in my sample space is just 2. My event, we can call it E for right now. We just want to know the outcome or the probability of landing tails. So the number of outcomes in my event is 1. So we have the sample space, which has 2 outcomes, heads and tails. My event, I want to know the probability of landing tails, so that's just 1 outcome. So the probability of landing tails would just be 1 out of 2, or 1 over 2, or 50% chance. So you place the number of your event over the number of your sample space.
That was easy.
Let's try another one. All right, so we have a single die that is rolled. What is the probability of landing a number greater than 2?
4.
All right, all right. So let's see if she is on point.
It's 1 over 4.
All right. So let's go through the process. So let's not forget when you talk about a die, a single die, for those of you who have played board games, hopefully, you know, saw you playing with die. So that's what we're looking at. You have 1, 2, 3, 4, 5, and 6. So that's our sample space. And so that means the number of my sample space is 6. And don't forget that that's 6 means I have 6 outcomes. You know, these 6s don't have anything to do with each other. This 6 and this 6 have nothing to do with each other. If I had 1, 2, 3, 4, 5, 10, then the number of outcomes is still going to be 6. So I want you to think just because I end in the 6 that my number of outcomes has to be 6. It's all about how many outcomes do you have. That's the number of elements in your sample space, number of outcomes in your sample space.
I can already see I missed it.
Now your event, we're talking about number greater than 2. So you're looking at 3, 4, 5, and 6. All right, so the number in the event would be 4 because I have 4 outcomes.
4 over 6.
You got it. And so the probability of my event occurring, like she mentioned, is 4 over 6. And then you reduce it, get your ability to reduce. So 2/3, you got a 2 out of 3 chance of getting a number greater than 2. All right. Questions on that before we look at the next one?
Nope.
A pair of dice is rolled. Compute the probability of rolling a 7, and then compute the probability of rolling snake eyes. All right, and then when it comes to snake eyes, the book did tell you that's rolling a 2. All right. So first thing we want to do is establish a sample space. Matter of fact, I don't need the whole sample space, but I need the number of my sample space. So when we look at what we're having here, is that we're going to have die 1 and die 2. We're going to roll them. And there's a possibility that I could have a 1 for die 1, a 1 for die 2. I could have 1 for die 1, but then 2 for die 2, 1 here, 3 here, and so on. And that can, give me any type of combination. So the way I would establish, so basically I don't want to have to list out all of my combinations in order to know the number of combinations that I have at my disposal. So what we'll do is whenever you have something like this, die 1, I know that I have 6 options. Die 2, I have 6 options. So you just multiply those options together, and that's 36 total possible outcomes. So whenever you have just only one option can be chosen. So if I roll a die, there's no way for me to roll a 1 and a 2 at the same time for die 1. Oh no, hold on, let me go back. Okay, great. So I missed to hit a button. So D1, if D1, you only can choose one value there. D2, only can choose one value there. So if that's the case, I can just multiply those together and get my 36 possible outcomes. Let's say if I was rolling a funky die and I had 8 outcomes that were possible, on my second die, then I would just multiply them together and get 48. So that's the way we can always do that. Total number of outcomes in each, multiply them together, lets you know all of the possible outcomes that can be created. So now when I look at my event, talking about rolling a 7, so now we have to look at all the different ways that a 7 could be rolled. So looking at die 1 and die 2, I could roll 1 here, 6 here, 2 here, 5, 3, 4. Now, if I roll a 3 for die 1 and a 4 for die 2, that is not the same thing as rolling a 4 for die 1 and a 3 for die 2. So I can just reverse my numbers. And I have 6 possible event outcomes. All right. Questions on that before we look to finish off the problem?
Nope.
All right. So the probability of your event is going to be 6 over 36, which is 1 over 6. All right. So rolling snake eyes, and we already said that that's the same thing as rolling a 2. We already know our sample space is 36. We're still dealing with the same problem. But but when we look at our event, you ask yourself how many different ways can you roll a 2? And there's only one way, excuse me. That's just when both of them are 1. So the probability of rolling snake eyes is just 1 out of 36. All right, questions before we look at least one more example?
Nope.
All right, suppose a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl using the empirical method. Compute the probability of 2 boys and 1 girl, having 2 boys and 1 girl, left out having, using the classical method. All right, I'll give you a chance to finish writing and then we'll do it. All right, so when we look at the empirical rule, all we would do is, let's say, the probability of 2 boys, 1 girl. We would take the 180 and place it over the 500. That was the first method we talked about, the empirical method. And that's 0.36. So remember that 180 and 500 came from the problem. There were 180 families. They had 2 boys and 1 girl. And there were a total of 500 families. So you take that 180 and place it over the 500. All right. So that's the empirical method. Now the classical method adds a little bit more to it. So we have to analyze what could occur. So we have firstborn, second, and then third. So you could start off with a boy first, then a boy second, or maybe a girl second. Then after you had a boy, you could have a boy or a girl. After you have a girl, once again, you could have a boy or a girl. Then it's possible you could have had a girl first, boy, girl, boy, girl, and boy, girl. So we have 8 different possible outcomes. So your sample space is going to be 8 because we have 8 possible outcomes. Now your event is having 2 boys and 1 girl. So here, 2 boys, 1 girl. Here, 2 boys, 1 girl. Here, I think that is it. All right. So the number of your event is going to be 3. Or let me do it like this. So 3 times is when we got 2 boys and 1 girl. 3 out of the 8. So once we have that, the probability of 2 boys and 1 girl would be 3/8. All right, questions. Oh, if they want the decimal, you just divide that out. That would be 0.375. So my math lab will let you know which one they want, whether they want fraction or the decimal. But I just went ahead and converted that to a decimal because we did that with the other one. You got that 0.36.
Easy peasy.
All right, cool. So that is 5.1. So as always, try the stuff out. See if you get stuck. See if you have any questions. Every day is the opportunity for questions. Always feel free to ask, and we will go from there. Any questions before we close out?
No,
All right. All right.
don't forget
So,
my email.
yep, I got you. I'm gonna hit you right after we close out. So, if that is good, I'm good. You guys have a great day, and I will see you on Thursday.
Thank you.
Thank you.